algorithm, graph coloring problem, then it will be basically nothing but it is modeling and solving the problem of the conflicts. Another such problems is about finding out the time slots for the examination. Now here in this particular scenario, two courses having the common students cannot be scheduled in the same time slot. So the two courses having the common students can basically be represented again with the help of the graph. So the graph is nothing but the modeling of the conflicts between courses such that the adjacent vertices like this can be scheduled in different slots. Hence, this way of representing the problem of university examination is nothing but modeling the conflicts, and then the graph coloring or the chromatic number of the graph is the minimum number of slots required to conduct the entire examination. So again, this is another such problem. So that means whenever there is a problem of a conflict, it can be modeled in the form of a graph, and the chromatic number of that particular graph will become the minimum number of slots or minimum number of time slots required to solve that particular problem. So hence, how this particular coloring is to be done in these graphs which are modeling different problems. For example, committee scheduling with a minimum number of slots. Similarly, examination to be conducted with a minimum number of slots. So that kind of particular problem can easily be modeled in a form of a graph, and that will basically captures the conflict relation, and then basically the chromatic number, that means what is basically how the coloring is to be done in that particular graph, and that number of colors, minimum number of colors required, that is called chromatic number of a graph, will tell what is basically the best possible way that particular problem can be solved. Another such problem of coloring arises in a map coloring. So coloring the regions of a map with different colors on the regions with a common boundary is another such example called map coloring problem. So on the left here we can see that it has 5 regions, 1, 2, 3, 4, 5, but the constraint that the adjacent region should not receive the same color, adjacent region should receive the different colors. So the adjacent regions are receiving different colors that we have already shown you, so that no two regions which are basically having the common boundary are receiving the same color, they are receiving different colors. So how many colors are required? 1, 2, then this is already done, 3 and 4 different colors are required to basically map this 5 region map. This particular map can also be represented in a form of a graph, where these regions are represented as a nodes, regions of a map, and edges are the adjacency relation between the regions. So having modeled this particular graph, now we apply how many minimum number of colors required in this particular vertex coloring of this graph. That will be the solution for map coloring region. So this particular labeling of these vertices, or we also say it's a coloring of the vertices, will be the context for coloring problems. Vertex coloring, K coloring of a graph G is a labeling function f which maps vertices of G to S, where S is basically a set of K different values. These are called labels, or these labels are the colors. The vertices of one color will form the color class. So a K coloring is a proper if adjacent vertices have different labels. A graph is K colorable if it has a proper K coloring. The chromatic number chi of G is the least K such that G is 3 colorable. So take this particular example. So let us take a graph of having 4 vertices. Now we do the labeling. So let us call it as labels. So let us say how many labels are required for this particular graph G. This label is proper if the adjacent vertices are receiving different colors. For example, if we color and say that this particular color is having label 1, then these two adjacent vertices cannot receive the same color. So let us give it another color and let us call it as 2. This vertex is concerned, this vertex can also be colored with the same color 2, and yet it is a proper coloring. Now as far as this vertex is concerned, this vertex cannot be colored with color number 2, so it can be colored with color number 1. So with only 2 labels we can basically color these particular graphs. So that means labeling is nothing but these set of vertices, let us say A, B, C, D. They are being mapped to a set S, and that S is 1/2, and we have shown this particular mapping here in this particular graph. So we have found out a proper here 2 proper to labeling. This particular labeling, whether it represents these numbers or if these numbers are immaterial or not having any significance, then we can call them as a color. So this is called proper because you see every 2 adjacent vertices are receiving different colors. Hence this particular coloring is called proper. 2 coloring is required because with 1 color you cannot color this particular graph. So minimum 2 colors are required. So we have obtained a proper 2 coloring of this particular graph, and let us revisit the definition again. So a K coloring of a graph G is the labeling which is nothing but a function of vertices of G which will map to some set of labels, let us call K different labels. So these labels are called colors. Why? Because their values are immaterial from which set they belong, that also is not having any significance. So let us call it as colors. The vertices of one color, for example the vertices having color 1 are represented as A and D. Similarly the vertices of color 2 are represented as B comma C, and they are called color classes. So the vertices of one color is called the color class. So in this example we have shown you two color classes, 1 and 2. Now a K coloring is a proper if adjacent vertices have different labels. Here you can see vertex A and B, they are adjacent but they have colors or labels 1 and 2, they are not having same. Hence any two vertices, any pair of vertices which are adjacent, if you pick, they may be receiving different colors or different labels. Hence this coloring is proper. So a graph is K colorable if it has a proper K coloring. So we have shown a proper 2 coloring of a graph, hence this particular graph is 2 colorable. Now the chromatic number chi of G is the least K such that G is K colorable. So here we have taken the value 2, hence chi of G is 2. So the chromatic number of this particular graph which we have shown you, which we have taken in this particular example, is 2, because this is the least value. You can also color with 3 number of colors, you can also color with 4 different numbers of colors, but this is the least of these all. Hence this particular least value K such that this graph is K colorable, this value becomes 2 here in this particular example. So a graph is K colorable if it has proper K coloring. The chromatic number chi of G is the least K such that G is K colorable. In the proper coloring, each color class is an independent set. So a graph is K colorable if and only if vertices of a graph G is the union of K independent sets. Take this particular graph, same graph which we have taken up. So it required 2 different, so it's a 2 colorable graph. So chromatic number of this particular graph we have shown is 2. So that means this is color 1, these adjacent will receive the second color, this is again receives color. So we can partition or we can collect the color class. So all the vertices of having same set of colors is an independent set. Why? Because they don't have any edge. If they have an edge or they are adjacent, that then they cannot receive the same color. Hence, so each color class represents an independent set. So here this particular graph has 2 independent sets. Why? Because its chromatic number is 2. So a K colorable and K partite sets have the same meaning. The usage of these two terms is slightly different. Often K partite is a structural hypothesis, while K colorable is the result of an optimization problem that we will see further. Let us take the example of a 2 colorable graphs. So a graph is 2 colorable if it is bipartite. Let us see this particular bipartite graph. So this is C4. So this is 2 colorable, means we should be able to color this particular graph in 2 different colors. For example, this is the adjacent, so it cannot be red, so we have turned it to other color. This is also adjacent to red, it is turned to the other color. This can be red, so these 2 colors are required. So this graph is 2 colorable, or the chromatic number of C4 is equal to 2. Hence this is a bipartite graph. So 2 colorable graphs are bipartite graph. Now this is a C5 graph. Let us start the coloring and see how many minimum number of colors can be colored with 2 different colors. Let us color it with this color. These 2 adjacent nodes cannot receive this particular color 1. which we have assigned. This particular node is not adjacent, so it can also be colored with, hence this cannot be colored. Let us take another color to color the remaining vertices. Since this is color 1, so we have chosen the another color. So this is the color number 2. This also can receive the same color. Why? Because they are not adjacent either to the second color nor to the first color. As far as this is concerned, neither it can be colored with the color number 1 nor it can be colored with color number 2. So we have to select from the palette another color. So C3 required how many colors? 3 different colors. So this particular graph is 3 colorable. Why? Because we cannot color this graph in with 2 colors, hence minimum number of colors required to color this particular graph is 3, hence it is called 3 colorable. Similarly, let us draw a Peterson graph and then we will see this is also the isomorphic to the Peterson graph. So another way to represent it. But let us see this particular and start the coloring. How many colors we need to color this Peterson graph? Let us take this particular vertex and color with color number 1. This is adjacent, it cannot be receiving the same colors. Let us color these 2 vertices again with the same color. Then let us choose another color so that the remaining vertices. Now this is adjacent to this red, so it should receive a different color. So different color can be used to color this particular graph. Similarly, we can color these 2 vertices also. Why? Because they are not adjacent, they may basically get the same color. As far as these nodes are concerned, they cannot be colored with the second color. Similarly, these colors, these 2 nodes, they may be colored. Why? Because they are not adjacent to these colors. Now we require another third color to color the remaining part of the vertices. This can be colored with the third color. So 3 colors. So this graph is 3 colorable, or the chromatic number of Peterson graph is equal to 3 that we have seen. So these graphs are called 3 colorable, while bipartite graphs are called 2 colorable graphs. So with this, let us see the definition of a chromatic number of a graph. A graph G is K chromatic if the chi value of G is equal to K, that we have already seen. A proper K coloring of a K chromatic graph is an optimal coloring. Again I am explaining it. So if a graph is K chromatic graph, that means the chromatic number of a particular graph is, let us say, K, if it is given. If we obtain a proper K coloring of a graph with a chromatic number K, then it is called an optimal coloring. So optimal coloring is nothing but finding out a proper K coloring of a K chromatic graph. Is an optimal K coloring. Instead of K optimal, you can say that for a graph having the chi value is equal to K, this particular coloring is the optimal coloring. Let us see the K critical graphs for small values of K. Now if we take a subset of a graph G, let us call it as H, and the chromatic value of every subset of a graph G, that is H, is always less, and then for every proper subgraph H of G, then G is called color critical or a K critical graph. So again I am repeating, let us take a graph G whose chromatic number of a graph is K, and every subset H of that particular graph is having the chromatic value less than K or less than that chromatic value of this particular graph G, then G is color critical or it is called K critical. Let us understand this particular concept. So let us take a graph K2. K2 is 2 vertices. How many colors are required? Obviously this can be colored with 1, this is 2. So the chromatic number of K2 is 2. If you take a subset will be K1. So the chromatic number of K1 is 1, and that is less than K2. So the proper coloring needs at least 2 colors of a graph if and only the graph has an edge. Thus K2 is the only 2 critical graph here. Similarly K1 is only 1 critical graph. Since 2 colorable is the same as the bipartite set, or is the same as bipartite, so it will characterize the bipartite, means it will imply that 3 critical graphs are having the odd cycles. We can test 2 colorability of a graph by computing the distances from the vertex X. So capital X and capital Y, there are 2 big sets which we have obtained, where all the set of vertices U which are basically having the distance from X is the even parity, is basically forming an X set. Similarly the Y set is all such pair of all such vertices, let us call it as again V, whose distance from X is always odd in parity. So we will obtain 2 different sets, or we obtain a bipartition of a particular graph. Hence this particular graph is a bipartite graph, and each X is nothing but they are the independent sets. Now there is no good characterization of 4 critical graphs, or a test for 3 colorability is known to us. Let us take another definition, the clique number. So the clique number of a graph is little omega g of a graph is the maximum size of pairwise adjacent vertices in a graph. Earlier we have already given the alpha g is the independence number of a graph G, that is the number of independent sets or a maximum number of independent sets available in the particular graph. So with this particular introduction of that concepts, let us take a proposition for every graph G, chi of G, or a chromatic number of graph G is at least omega G. So that means if a graph has a clique, if a graph has a clique of size omega G, now clique, whenever clique is there, you can obtain, or you know that the chromatic number of a clique is n, or basically the size of the clique. You cannot obtain a proper coloring with less than that number of vertices of that particular clique. Hence the coloring which you are obtaining should contain at least the size of that particular clique. Hence this particular bound is proved. The second bound says that each color class, that means after obtaining the coloring, we collect the independent sets in the form of the color class, and alpha G will indicate the number of independent sets. So at least that many number of colors are required because each independent set will be given a separate color. So alpha g different colors are required. Hence total number of vertices are ng. If we divide, then at least that many number of colors will be required. Hence the second bound is also proved. Now let us see that this particular bound, how good this bound is in the terms of tightness. So chi of g may exceed omega g in this particular construction of a graph. Let us take for the values of r is greater than 2, greater than or equal to 2. So if we take r is equal to 2, then it will form a cycle, odd cycle. C2r plus 1 becomes an odd cycle C5, and Ks is any complete graph which is represented here. Now union operation we have defined earlier of two graphs is nothing but all the vertices of these two graphs are adjacent to each other. So if that is the condition, then every vertex will be adjacent to all the vertices of Ks. Similarly, this vertex also will be adjacent to all the other vertices of Ks. This also will be adjacent So let us see how many colors are required. Definitely this particular graph G is going to exceed this particular value. Why? Because every vertex of C2R plus 1 is adjacent to Ks. So more than omega of G, that is, this is the complete graph, that many number of colors are required. Let us see how many different colors are required. Now here you can see that this is an odd cycle. It requires how many colors? 3 colors, and this requires S colors. So obviously the chromatic number of this particular graph will be S plus 3, is at least this particular value will be there. Hence we conclude that in this particular scenario is strictly greater than the size of the click. So I told you that we are looking up this particular bound, how good this particular bound is. So for some of the graphs here the bound is quite loose. Why? Because it is strictly greater than omega G. Now let us see, we will see further that a particular graph where this particular bound is tight or equal, hence the coloring will be looked upon. Now let us take the definition of a Cartesian product of two graphs G and H, which is represented by this particular symbol. Cartesian product of the two graphs is a graph with a vertex set Vg cross, or a Cartesian product vertex set of H, which is specified by putting uv adjacent to u prime v prime if and only if u is equal to u prime and v prime v prime will have an edge in H. Similarly, v is equal to v prime and u prime has an edge in G. So this is the example of such construction, but let us see another example. So this is C3 cycle, and let us take a C2 cycle and let us draw a cross product of C3, Cartesian product C3 and C2. So this particular vertex, if we take a Cartesian product, what will happen? Let us see. that these two vertices will join and they will basically form this one, and then again another pair of vertices, and this is also joined. So as far as these definitions are concerned, u and u prime, this is, let us say, u and this is u prime. So u and u prime is equal, and v and v prime, let us say that this is v prime and this is, let us say, v. So v and v prime has an edge, so that will represent something here, no, something like u and u, v and v prime. So let us see in this particular example x, y, z, this is, you know, that C3 cycle, 1, 2, 3, 4, this is C4. So let us take this particular example, and we will see in this particular example the Cartesian product of these particular graphs. So you see that this particular cycle is repeated at every pair of vertices, and this particular cycle is also repeated on the other side, and that becomes a Cartesian product. So having defined this particular Cartesian product, then let us see the proposition given by Ising that the chromatic number of the Cartesian product of two graphs is nothing but the maximum of the chromatic number of the graph G and the chromatic number of graph H. Now let us find out the upper bounds in terms of the colorability. So most upper bounds on the chromatic number come from the algorithm that produce the colorings. For example, assigning distinct colors to the vertices will yield that the chromatic number of G is at most Ng, in the sense that if we are given a graph, let us say that this particular graph here is K3, then you require how many different colors? That is nothing but the number of the vertices, that becomes equal. But if the graph is not complete, then what will happen? Then this is not equal to Ng, but it is less than Ng. For example, if there is no edge, so you can color using two colors only, that is not with the three colors. So that means then chi of G is basically not equal to Ng, but it is less than Ng. So this particular makes a possibility to find out the bound. So this bound is the best possible when the graph is the complete graph, that is equal to n. But we can improve this particular best possible bound with another bound that is always at least as good. Why? Because if we say that the upper bound of a chromatic number is Ng, that means we haven't seen inside the structure of that particular graph, and we have assumed the structure of complete graph, and we have established a bound. So if the graph is not a complete graph, then a better bound is to be ascertained. So we can do better by coloring the vertices in some order and always using the least available color. Greedy coloring algorithm. The greedy coloring relative to the vertex ordering, that is V1, V2 and so on up to Vn, a particular ordering of the vertices of a graph G, is obtained by coloring the vertices in this particular given order, assigning to a vertex Vi the smallest index color not already used on its lower index neighbors. So we are going to give you the first algorithm for coloring, and this is called greedy coloring algorithm. Then we will check the bound which we obtain using this particular greedy coloring. How good the bound is, we will know that once we compare it with the chromatic number of a graph G. Then we will see how we can improve this particular algorithm and more insight in the graph coloring. So again I am explaining this particular algorithm. A greedy coloring algorithm is related to the vertex ordering. Again I am taking, let us take the simple graph V1, V2, V3. So a particular ordering, let us say we say that V2, then V3 and V1, and we want to color in this order. First we have to order the vertices and then we will be coloring them in the same order. So let us, we have obtained a particular order. Now according to greedy coloring algorithm, we will assign to Vi, the smallest indexed color. So we will obtain the colors as the indexes. For example, color number 1, 2, 3, 4 and so on. So one may represent red, blue, green and so on. So colors are also indexed and vertices are also in particular order. Now let us see that greedy coloring algorithm says that a greedy coloring relative to the vertex ordering is obtained by coloring the vertices in that same order, assigning the vertex Vi the smallest indexed color not already used on its lower indexed neighbors. So smallest index colors, that means we will pick the colors from a particular index, that is a lower index colors which are not applied earlier to its neighbor will be applied to that particular vertex. Let us take this particular example. So let us, we have the coloring colors 1, 2 and 3. They are indexed. Now vertices relative to the given order, let us say these orders are V2, V3 and V1. So first we have to color V2. We will color V2 by picking the least indexed color which is not used in its lower indexed neighbors. One is never used. So let us color with this particular vertex with the color number 1. Now comes to V3. V3 is a neighbor of V2 who has already used lowest indexed or smallest index color 1. So the next smallest index color which is not used by the neighbor is color number 2. So V3 will be colored with color number 2. As far as V1 is concerned, V1 is neighbor to V2 and V3, both are its neighbors. So the V2 and V3 have already used color number 1 and 2, that means the smallest index color which is not used by the neighbor is color number 3. So this can be colored with 3. So this particular coloring is called a greedy coloring. So this particular graph is also explaining the greedy coloring algorithm. Here we are given 5 node graph, let us call it as G, and we are given the vertices in this particular relative order 1, 2, 3, 4 and 5. So the vertices are given in this order and we have to color relative to this particular order in this algorithm. Similarly, we are also given the indexes of the colors 1, 2, 3, 4 and so on. Starting the algorithm, what it does, vertex 1 will be colored first with the smallest indexed color not used by the neighbor of one earlier. So, the color number 1 will be assigned. Second vertex is vertex number 2. Vertex number 2 is the neighbor of vertex number 1. So, the smallest index color which is not used by the neighbor of 2 is 3, is basically the second index color, so which is assigned to that particular vertex. Similarly, the vertex number 3 in that order. Now, vertex number 3 is neighbor to the earlier used colors by their neighbors, that is 1 and 2 are its neighbors. 1 and 2 color is already used, so smallest color index which is not used by the neighbor of 3 is 3 itself. So, 3 will be colored to this particular vertex. Now, coming vertex number 4. Now, vertex number 4, the neighbors of 4 who have used the colors earlier are 3 and 2. So, 3 cannot be used and 2 cannot be used. So, the smallest index color which is available is 1. So, 1 will be assigned to this particular vertex. Finally, we have to come to 5. So, vertex number 5, its neighbor are 3 and 4. Let us see what colors 3 and 4 are assigned. So, 3 and 4 are assigned this color and this color. So, the smallest index color which is not used by the neighbors of 5 is 2. So, 2 will be assigned here. So, this becomes a greedy coloring algorithm. Now, let us see the proposition which will estimate the basically performance in terms of the bound of this greedy coloring algorithm. This greedy coloring algorithm will give the bound which says that the chromatic number of a particular graph is less than or equal to the maximum degree of a graph plus 1. Let us see the proof. Proof says that for a relative vertex ordering, each vertex has at most maximum degree earlier neighbors. So, the greedy coloring cannot be forced to use more than maximum degree plus 1 number of colors. Hence, this proves constructively that the chromatic number of a graph is bounded by or is at most maximum degree of a graph plus 1. Now, this maximum degree plus 1 bound is the worst upper bound that the greedy coloring algorithm could produce, although this becomes optimal for a complete graph and odd cycles. Now, choosing this particular greedy coloring algorithm depends upon choosing the vertex ordering. So, if the vertex ordering is chosen very carefully, it will improve this particular bound further. Now, one heuristic which will be applied here is that if we order the vertices according to the degree sequence, so that the highest degree vertices are placed ahead or in the beginning in the sequence, and the next higher degree will be placed and so on, because if the highest degree vertex is placed, there will be no other neighbor before it. Hence, you can easily start the color, and obviously the number of colors required will be quite less, or it will improve this particular bound of the greedy coloring algorithm. Let us see this particular heuristic which is given by Welch Powell, and hence the proposition which will give you a further modification in the bound. So if a graph G has a degree sequence, d1 is greater than or equal to d2 is greater than and so on up to dn. That means non-increasing order of the degree sequence of a graph if it is given. That means vertices are ordered in this particular degree sequence. Then when we apply the greedy coloring on this particular relative vertex ordering of this degree sequence, so that vertex V1 is having the highest degree is placed first, then second, and so on. Then this particular kind of coloring or using this heuristic, which is called Welch-Powell heuristic, let us estimate that it gives 1 plus max of I, minimum of di and I minus 1, and this particular bound is better than maximum degree plus 1, some of the situations. Now let us prove this. So we apply greedy coloring to the vertices in the non-increasing order of the degrees. Now when we color ith vertex I, it has at most either the di, or if the highest degree is placed before it is I minus 1 is lesser than the di, then the minimum of either the degree or the I minus 1. So I minus 1 says that the highest degree is, let us say that V1, node is V1, so V1 is placed, so before V1 there is no other neighbor, hence di will be not used. So I minus 1, that means I means the index I is 1, so the 0 index colors will be used. So minimum of that these two smallest index and the degree values are taken together in Welch-Powell heuristics. So again I am repeating that vertex I has at most minimum of di and I minus 1 earlier neighbors. So at most this many number of colors appear on other neighbors, hence the color we assign to Vi is at most 1 plus minimum of di and I minus 1. This holds for each vertex. So if we maximize over I to obtain the upper bound on the maximum number of colors used, will be this particular bound that we have already proved. Now let us see the remarks on these two discussions. That is, first we have obtained a greedy coloring whose bound was big delta G plus 1, and then we have seen the Welch-Powell where it is 1 plus max of I, min of di and I minus 1. So the bound is always at most 1 plus maximum degree of a graph. So this is always at least as good as the proposition which we have seen. So that means this particular bound is at least as good as the earlier bound which we have seen. It gives optimal upper bound for a particular example that we have seen, the union of odd cycle and the complete graph, while 1 plus maximum degree does not give it. So in proposition 5.1.14, that is Welch-Powell, we use the greedy coloring with the well chosen ordering. In fact, every graph has some vertex ordering for which the greedy coloring uses only the optimal number of colors, but it is very hard to find out such an ordering, hence the graph coloring problem. To find out an optimal coloring through an algorithm is a bit hard, it's not an easy algorithm. So our next example introduces a class of graphs where such an ordering is easy to find. which ordering means that ordering which gives an optimal coloring through the greedy coloring. So the ordering produces a coloring that achieves the equality in the bound, that is chi of g is equal to little omega of g. So that we will see. So this kind of graph or this kind of ordering which we are talking about here, we can obtain using a particular kind of graph which are called an interval graph, and these interval graphs are basically, if we see the problem of a register allocation in the compiler or in the which compiler does, normally it uses the register allocation through the understanding how it is going to be used in the programs, and that is represented in the form of interval graphs, and that interval graphs will give the vertex ordering, and that ordering is basically the optimal, gives an optimal coloring through the greedy coloring. Let us see all that things in this example. So a computer program stores the values of its variables in the memory. For arithmetic computations, the values must be entered in easily accessed locations which are called registers. Registers are expensive, so we want to use them efficiently. Two variables are never used simultaneously, then we allocate them to the same register. For each variable, we compute the first and last time when it is used. A variable is active during the interval between these times. This is represented in the form of a graph which is called interval graph. So we define a graph whose vertices are the variables. Two vertices are adjacent if they are active at the common time. The number of registers needed is the chromatic number of this graph. The time when the variable is active is an interval, so we obtain a special type of representation for the graph which is called a interval graph. So let us take the example that given this particular graph here is called an interval graph, and the intervals are given in this particular manner. So the vertex ordering corresponding to this particular interval graph becomes A, then B, then C, then D, then E, then F, then G, then H. So this particular vertex ordering C is concerned, C is the neighbor of B, so C cannot be given this particular color, but C can be given the smallest index color, that is 1. As far as D is concerned, D is the neighbor of C and B, so C is basically having the color number 1, B is having 2, so the third color is given to D. Similarly, E is concerned, E is a neighbor of C and D, so C is having color 1, it cannot be used color 1, so color 2 is the smallest one, so color 2 will be assigned to E. As far as F is concerned, F will be given red, and all the colors will be assigned as we have shown in this particular figure. Now this particular coloring which we have obtained in this particular vertex ordering in the interval graph is optimal, and that uses only 4 colors. Now we will see the proposition which says that if G is an interval graph, then chromatic number of a graph is equal to omega G. That means we can color with only the click value of that particular graph, hence this becomes optimal. Why? Because we have seen that it is at least omega G, now it becomes equal to omega G, hence this particular coloring is optimal for interval graphs. Let us see the proof. Order the vertices according to the left endpoints of the intervals in the interval representation that we have already seen earlier in the example. Apply the greedy coloring and suppose that x receives k maximum colors assigned. Since x does not receive a smaller color, left end point A of its interval belongs to the interval that already have the colors 1 through k minus 1. These intervals all share the point A, and we have k clique consisting of x and the neighbors of x with colors 1 through k minus 1. Hence omega g is at least k, and that is basically at least, or that is less than chromatic number of that particular graph. Since chromatic number is always greater than omega g, greater than or equal to omega g always, so if we take both these equations, then this particular coloring is optimal, hence it is proved. Now remark, the greedy coloring algorithm runs rapidly. It is online in the sense that it produces a proper coloring even if it sees only one new vertex at each step, and must color it with no option to change earlier colors. For random vertex ordering in a random graph, greedy coloring almost always uses only about twice as many colors as the minimum. Although with a bad ordering, it may use many colors on a tree. Conclusion. In this lecture, we have discussed k coloring of a graph, optimal coloring, clique number, Cartesian product, the upper bounds, that is with reference to the greedy coloring. We have also seen an interval graph based coloring and example which is based on it, that is about register allocation. In upcoming lectures, we will discuss the Brooks theorem. Thank you.